And it is a massive, massive issue when we're looking at carbonyl chemistry. Okay? We're running in almost both circumstances, both potentially under acidic or basic conditions. Think back to the acetal. Okay? Under the acetal formation, we ran under acidic conditions. That was the only way we could make the acetal. If we ran under basic conditions, we stopped at the hemiacetal. We can't go any further. Okay? And that has to do with looking at each of the individual steps of your mechanism. Okay? So things to evaluate while you're looking at a mechanism is decide what conditions you're running under. Maybe the question tells you, or maybe like this case, it was intentionally vague and says, leave it up to you, you figure out what conditions you're running under, and then make sure you follow those rules. If we're running under acidic conditions, that necessarily means what is present? H+. Which means you need to deal with that H+ at each potential step of the reaction. Right? Which also means at no point should we ever see a minus charge. Because a minus charge means base. So if you've decided you're under acidic conditions, you need to make sure that you never form a negative charge. Right? Just because one group was nice enough to put it up on the wall, we'll point out their structure. Very first step, I like the idea, they're showing the resonance with that, so we can see the positive carbonyl, the positive carbon of our carbonyl. That's nice. They then had the nitrogen attack. The nitrogen's a good nucleophile, why not? What did they produce? Now look at the next step. Once the
Negative oxygen.
we have a negative oxygen. What's the issue with a negative oxygen? That is a strong base. If we're in acidic conditions, does that form? Right. You can't stop at any one of these intermediates because all of those are intermediates. So if you want to run under acidic conditions, where do you start under acidic conditions? At the very beginning. You can't switch partway through your mechanism to be under acidic conditions. Or partway through now switch it to basic. Okay, with all of these reactions, you start acidic or you start basic. Okay, these are not separate steps. To get a separate step, we must be able to isolate one of those compounds. And your very first drawing here is suggesting that it's not acidic. That structure is unstable. That's effectively an acetal. And what happens with our acetals? Decompose back to our carbonyls. It's a slightly different form of the acetal because we're using a nitrogen, but it's the same idea. Right? So if we're going to decide we're running under acidic conditions, that oxygen can't be negative. So what could we change about this mechanism to make sure that negative oxygen never appears? Let's protonate the oxygen before the nitrogen attacks. Right? So it's changing the sequence or the order in which you run the reaction. So if we look at this, if we say H+ comes in, we protonate our carbonyl first. We've got a positively charged structure. If we look at its resonance, we still have a positively charged structure. At no point do we see that negative charge show up. We're now running under acidic conditions, and we haven't invalidated our assumptions. Okay? As we continue to push it through, say there's another issue with the structure drawn here. What's that issue? Overall charge of your starting material is what? Neutral. Overall charge of what's drawn? Negative. We're missing a charge. You were aware of the chemistry when you drew it out because what did you end up doing? You had the nitrogen take a pair of electrons away from the hydrogen. Why did it take the electrons away? Because the nitrogen was positively charged. Okay? You're following the charges all the way through. So yeah, I understand that it takes time to draw out those charges. But if you draw them out, you can track your chemistry as opposed to just saying, oh crap, I don't know what to do now. Follow the positive and negative. Next question, it's going to be an awesome question. We've shown what type of reaction in this step. It's an acid-base step. Okay, we can add a little bit more information to it. It's an intramolecular acid-base reaction. What does intramolecular mean?
Inside the molecule.
Happens within the molecule. How often do we get cyclobutane rings forming? Butane. Not very often at all. Why not? The bond angles are too tight to go through and do that. Look at the transition state of what's happening here. We have one atom, a second atom, a third atom, a fourth atom. For that oxygen to react with that hydrogen, what are we forming?
A ring.
Effectively, a four-membered ring. Is that likely to occur? No. Where is the oxygen going to pick up a hydrogen? Well, it already picked it up, so we don't have to stress there. Where can this nitrogen dump that hydrogen off to? Something in solution. Okay, and this drives people up the wall. Okay, it drives me up the wall that you have to be that specific about what's picking it up. You don't need that specificity. You just know that that hydrogen is stupidly, ridiculously acidic because nitrogen is positively charged. So something with electrons will pick up that hydrogen. I don't care what that something is. As long as something is there, it'll pick up that hydrogen. Right? So we've got an acid-base reaction. You can push further on. You'll end up eventually with this nice transition state. What happens now? Okay, well, we might want to have the nitrogen form our double bond. We know it needs to happen. But to do that, that carbon needs to be positive or missing electrons. It's not missing those electrons yet. So what did you guys do? Protonated the oxygen because acidic conditions and we want a good leaving group. Now that we've got it protonated, it can leave. You guys showed it leaving on its own. Why? It's not just because H2O is a good leaving group, because if I draw out another structure here.
And the electrons from the carbon anyway.
I won't ever form a primary carbocation. What kind of carbocation are we making here? It's roughly a tertiary. Is a tertiary carbocation relatively stable?
Yes.
Yeah. So it makes sense for the water to leave on its own as a mechanistic step, followed by the nitrogen sharing its electrons, forming our double bond. Good job, by the way, when you went through and did that. You didn't pull off the hydrogen beforehand. Why would it have been a problem if you pulled off the hydrogen beforehand? Okay. We're not ending up with our acidic structure. Okay, we're under acidic conditions. To pull the hydrogen off of this, we would have had to make a negatively charged species. Can't do that because we're under acidic conditions. Okay? With our nitrogen nucleophiles, much like our oxygen nucleophiles, we tend to favor the acidic mechanism. Okay, we're effectively doing acetals, but with nitrogen. And in the case of nitrogen, as the previous slide said, what we're looking at is a wickedly strong nucleophile. It is so strong that I don't need a second nucleophilic atom to attack that carbon. The nitrogen will do it twice. Whereas with oxygen, it could only do it once because it wasn't a strong enough nucleophile. The net result when we go through and run these reactions with nitrogen is that we can completely exchange an oxygen for the nitrogen. What is the proper mechanism? I can tell you right now, all of the ones that have been drawn up have had issues. Okay? You should now be able to go through and critique those issues and point out where something was wrong. You guys want time to poke around at that, or you want to move forward?
You said that in neutral conditions, there should be strong acid or base.
So when we go through and deal with neutral conditions, we want to make sure at no point do we form a strong acid or a strong base. So neutral conditions are very kind of hard to watch for because you will end up forming positives and negatives throughout the mechanism. You just have to be careful with your approach. Okay, very careful with that approach. If we go under strongly basic conditions, we're going to overall have negative charges because we're adding a negatively charged species to start with. Okay?
But I run under neutral condition, and during my mechanism, I have like one oxygen
So,
negative. Is that
what
correct?
conditions do we run with our nitrogens? We run under acidic conditions. That is how our nitrogen will function best, under acidic conditions, just like our oxygen. When we formed our acetals, what conditions did we need to form our acetal appropriately? They needed to be acidic. Nitrogen's going to do the same thing. So when you draw out your mechanism, some people did it on their own and used neutral conditions relatively to go through and do that. It's possible, but you're going to find that you get very weak equilibriums and you probably won't get a lot of product being formed. If we run under basic conditions, we end up forming very bad leaving groups and we don't really get anything to happen either. The only thing that really works is under acidic conditions. Okay? Which brings up the next slide's question. What did we say about nitrogen? It is both a stronger nucleophile and a stronger base. Why is that problematic? If nitrogen is a stronger nucleophile, when we add that acid catalyst, what do we expect to have happen? The formation of NH4 positive. Do we have a nucleophile anymore? No. That reaction is in equilibrium. Just like the reaction of our carbonyl being in equilibrium with the acidified structure. How can we progress forwards if we never have the nucleophile? We add the acid as a catalyst, relatively small amounts. And when we draw out our mechanism, what we're evaluating is the productive steps forward. Are there other steps? Absolutely. Those steps are not productive. This is where this material, more so than any other point in the semester, becomes very challenging. Because what's going to end up happening is you will run into a wall, right, when you're trying to work out the mechanism. And I've talked to a lot of people already having problems with this. You run into a wall, can't figure out how to solve it because you never saw that problem before. That's because what you've been doing is you see the answer, oh, I know the answer. You never had to run into that wall of deciding where the positives and negatives are. This is why I keep talking about positives and negatives and thinking about how you work through these things. When you deal with the equilibrium reactions with carbonyls and all of these different nucleophiles, you are running strictly under equilibrium conditions, which means your reactions are going every which way of sideways. Right? There is no one direction forward. You have to try all 6 answers. One of them gets you to a standard product. What do the other ones do? Hurt your head. Deal with it. Okay? Organic chemistry is about running into a wall and moving forward. Okay? Picking up the pieces and trying again. There's a nice little letter, note, article thing that I keep meaning to track down and find about a student that thought back on their experiences while they were in organic chemistry and compared them to their experiences in med school. And going through that whole process. And they thought back and remembered organic chemistry and remembered leaving every exam in tears and watching everybody leave crying, and it was a horrible, horrible experience and they hated life and everything was horrible. They eventually went into med school, got accepted, and they went through and did all the process of med school. And what happened in med school when they started their rotations? They cried every single day. Why?
Because you run into walls.
Because you killed someone. That will happen. You have to be able to pick up and move around that and beyond that. Failing an exam means nothing in the grand scheme of things. Okay, so organic chemistry is rough, it's brutal, there's a lot of stuff going on, but it's getting you the skills to run into that wall, say, holy crap, life sucks, and I'm going to pick it up and try again. Okay? Oh crap, life sucks again. Pick it up and try again. It's about continually trying new ways to get forward. You need that skill. which is why I'm going to try and stop giving you answers, because I think that's what's happening. As you look at the answers and you say, oh, it makes sense. It's an answer. That's why it makes sense. Okay? So, off the soapbox, more practice, 8 minutes. Okay, let's go through and look at some answers here. We've got some interesting things popping up. So for that first one, hopefully you guys should have gotten this as an answer. Right? You should have had the double bond between the nitrogen and the carbon. That structure is referred to as an imine. And depending on the context of the situation you're looking at, it's also typically referred to as a Schiff base. Right? Because that nitrogen can do resonance to pick up more electrons. So it's just kind of a term coming out of this. That structure will be referred to as that. You're not responsible for naming those. Just be aware it might pop up in your reading. Next one. Ooh, that's an interesting question. We've got a carbonyl, but we actually have 2 nucleophiles. Which of those is more nucleophilic? How is the nitrogen more nucleophilic? If it's more electronegative, what is it going to do to its electrons? Hold them, which means won't act as the nucleophile. Which one's more electronegative? The oxygen atom is more electronegative. Okay, it's very easy to get these things backwards, so walk through it slowly. If oxygen's more electronegative, what does that do to its nucleophilic character? It goes down, which means what's our nucleophile? Which atom is our nucleophile? The nitrogen is what's going to go through and do our attack. If we propagate that out, we'll get pretty much the same thing that we see above, except instead of it being CH3, it is now NOH. Another random name to add into this. Oh crap, I can't remember this one. I think it's a hydroxylamine. Okay, again, not responsible for knowing the name of that functional group or anything like that. Just, it will pop up. Next one.
Wait, it will
Go ahead.
do rearrangement, so you will put the carbocation on the most stable?
Oh, shoot. Sorry, I totally didn't even look at the structure right. That's my fault. That's my fault. Yeah. Is that why you guys were frantically erasing?
Yeah. I'm like, oh crap, I put the
Sorry.
carbon in the wrong
No,
place.
that was totally my
Yeah,
bad.
that's bad. Okay.
Yeah, there's your hydroxylamine. Thank you for calling me out on that. Okay. So no shifts. There's no reason to shift because we never form a carbocation that can shift. Okay. Next part of this. What happens with your next product? I'm going to have to turn this one on its side. Okay. How many people have this as an answer? I know, looks a little weird, but
Is it always going to be a double bond though? I have that though attached to it.
so you just drew a single bond?
Yeah. Yeah.
When we go through and look at all of our nitrogen compounds, what happened to the double bond? Did we lose it?
No.
No, it stays. We do have the double bond. But maybe, just maybe, you didn't like this structure as it was drawn. What is wrong with this structure? Nitrogen is formally positive. Does nitrogen want to be positive?
No.
So what does it do? Not quite. It'll take the electrons from the carbon, from the pi bond, which means the nitrogen picks up a lone pair, and our carbon is now positive. What's the problem with a positive carbon? It's not stable. So something else is going on. What happens? It's not a shift. It's a, what was that? It's an elimination. Okay. What's our big difference? Why did the chemistry all of a sudden change? In our first example, our nucleophile was what functional group? Very first question. What was our nucleophilic functional group? An amine. Can you classify that amine for me? How many carbons are attached to that nitrogen? It's a primary amine. Let's move to now our next example. Our third one. What kind of amine do we have? We have a secondary amine. Because we've changed the bonds around the amine, or around our nitrogen, we've now lost the ability to kick off those hydrogens to form our full imine product. So what ends up happening is we sacrifice a hydrogen from a proximal carbon to give us the alkene. That then makes the nitrogen happy because now it's not positively charged. What functional group is this? It's an alkene and an amine, also known as an enamine. Okay. Really important for our carbonyl chemistry. Yeah, Lou?
How come the carbon didn't just take a hydrogen from the solution?
If it's acidic, so the carbon that you're referring to, I may need you to point.
The carbocation.
A carbocation? Okay. Hydrogen from solution, if it's under acidic conditions, what would I draw?
The H plus?
H plus, right? Okay, I agree. What happens when the H plus gets near the positive carbon?
Repels.
Like charge repulsion. Okay? So sometimes it's nice, sometimes it's not. Okay? So we don't have any way to stabilize that. We end up losing the hydrogen from the, I think it's an alpha carbon at that point, and we form our elimination product. Okay? Last one, and then I'll let you go. What's happening? Whoops. Well, you already knew it was an enamine. What's happening in that last one? What's the first reagent that you would add? Good job. That's the one piece that was added in there. The next one is the trickier one. Okay, you look at that next reaction. What's the most reactive thing there? Hydroxide. What does hydroxide act as? Okay, so we can run primarily with the base. Does anybody want to dispute it acting as a base? Could also act as a nucleophile. If it acts as a nucleophile, where would it attack? The carbon. Okay, our carbonylish carbon, or our imine carbon. Okay? And it would attack that carbon because the carbon is what charge? Partially positive. We'd end up with a structure similar to our acetals with an OH and a nitrogen. Okay, let's just leave it at that. Let's not try to make it too more complicated. Just like our acetals, this is going to decompose. Which way would it decompose? Which is the stronger nucleophile, nitrogen or oxygen? Nitrogen. So what happens? Nitrogen comes back down, reforms a double bond, kicks out the OH. Hydroxide is not acting as a nucleophile. Okay. Well, it's not acting as a nucleophile. What's it acting as? A base. So what do we need to find?
Hydrogen.
An acidic hydrogen. Let's take it a little bit further away from that because acidic brings in this connotation of, well, nothing looks acidic. Okay. What makes an acidic hydrogen? H plus. So what you need to find is the most positive hydrogen. Where's the most positive hydrogen in that structure? The electrons come in, and what can they do? Resonance to stabilize the loss of that hydrogen. The net result is we also put a negative charge on that carbon. Does that carbon want to be negatively charged? No. So what can it do? Negatively charged carbons are going to act as nucleophiles. We can run the reverse reaction. Bummer. So another option? can act as a base. Is there anything remotely acidic floating around in solution? We could run with water, or we could even run with more of the dinitrogen compound from our previous step. Remember, we're running these with billions of these molecules floating around in solution. It's not just one. All right? For the sake of our mechanism, we'll show water. What happens? That picks up a hydrogen, and we reform hydroxide. Oh, that wasn't all that bad at all. All right? So now let me erase all of that, because I'm definitely going to run out of space on this. And we would end up with this structure, right? Everybody happy with that? We just added the hydrogen. It's now an implied hydrogen. What's that? It has a hydrogen. Why did we pull off the first hydrogen? Because of hydroxide. Is the second hydrogen really any different than the first hydrogen? No. Why not? Let's see what happens. What happens if we take those electrons, whoops, and we put them here? We'd remove the hydrogen and we'd now have a triple bond. But now how many electrons would be around that nitrogen? Too many. So what happens? You could kick it back, or what are you suggesting, Lulu? Take the electrons and put them on that carbon. What's the result? A negatively charged carbon and what's that other species? Nitrous implies an oxygen. What's the formula? Maybe that'll help you. N2. You remember this analogy? Have no fear of ice-cold beer. What was the no? Nitrogen, because it's a diatomic molecule. What just happened? You eliminated nitrogen gas from the solution. That is a wicked, awesome leaving group. Incredibly stable. We still have that negative carbon. So is there something positive in solution it could pick up? We still have more water floating around in solution. Our negative can pick up another hydrogen. And we end up with nitrogen gas as a product and our cyclohexene that we started with. What type of reaction did we just do? Yes, keep going. Not substitution. Addition. No, dang it, that wasn't the one I wanted either. Try again. How many bonds to oxygen do we have? 2. How many bonds to oxygen do we have? 0. What did we do? We did a reduction. You now have another method to do a reduction without actually supplying a hydrogen nucleophile. All sorts of weird in that one. We supplied H+, and we were somehow actually able to do a reduction. Okay? This reduction method, just for the heck of it, because I ended up having to do it in grad school, not Wolf. I might be spelling his name wrong. It's known as the Wolff-Kitchener reduction, okay, which I've probably butchered the spelling on. But that's a Wolff-Kitchener reduction. Okay? Kind of a neat reaction. We take advantage of the nitrogen, and then we move to a new reagent. We say, well, I don't know what that reagent does, so try it. Keep adding it, see what happens. In the process of continuing to add it, we ended up forming something that is incredibly stable. What does all chemistry strive for? Something incredibly stable. The only way we can find that is if we keep pushing on it to see how that could possibly happen. It's that persistence that you need to build with this section of material. Okay, and you'll notice that at each and every single stage of this, we did not invalidate any electron pushing. Okay? Our electronegative atoms accepted electrons in all cases, or held electrons. Okay? So sorry,